Have you ever just stopped and wondered about the invisible magic that lets you stream a movie, or jump on a video call, or even just scroll through your phone? It all feels so seamless, right? Well, underneath that simplicity are two absolutely revolutionary technologies that completely re-engineered our wireless world. So let's pull back the curtain and see how it all really works. I mean, really think about it. You're in an airport, a stadium, some busy cafe. There are hundreds, maybe thousands of people, all on their devices, hammering the same Wi-Fi or cellular network. So why doesn't it all just collapse into a digital traffic jam? The answer lies in how we solved some of the oldest, most fundamental problems in radio. You see, for the longest time, wireless communication had two huge enemies. First, if signals used the same frequency, they'd just crash into each other and become gibberish. And second, signals would bounce off everything, walls, buildings, the ground, and arrive at your device as a confusing storm of echoes. We call that multipath. For decades, the best we could do was just try to fight this mess. But then, a couple of brilliant ideas changed absolutely everything. So, here's what we're going to cover. We'll start with that initial traffic jam in the airwaves. Then, we'll look at how a technology called OFDM brought some much-needed order. After that, we'll see how MIMO created a kind of spatial superhighway. We'll see how they work together as a perfect team, and finally, what it all means for the wireless world we live in today. Okay, so let's set the stage with that core problem. The airwaves are just naturally crowded and chaotic. Trying to send a single high-speed stream of data through this environment was like trying to shout a long, complicated sentence in a huge, echoing cathedral. By the time it gets to the other side, the message is completely garbled and lost. The first huge breakthrough came from this beautifully elegant idea called OFDM. Instead of shouting that one fast, fragile message, engineers had a thought. What if we broke it down into hundreds of slower, more robust messages and just sent them all at once? And that is the absolute heart of OFDM. It is a divide and conquer strategy. Picture one giant high-speed highway. And now imagine splitting it into hundreds of smaller, slower side streets. Each of those individual substreams is way slower, and that's key. It means each little piece of data is transmitted for a longer period of time, which makes it far, far more resilient to those echoes that would totally corrupt a single, faster stream. This really shows you just how clever OFDM is compared to the old way. The old methods, called FDM, kept radio channels separate by putting these huge, empty guard bands of spectrum between them. It was incredibly wasteful. But OFDM? It lets the channels actually overlap, packing them right next to each other to use every last bit of spectrum. So the big question is, how can they overlap without interfering? Well, the secret is this amazing mathematical property called orthogonality. The subcarriers are spaced out so precisely that at the exact frequency where one carrier hits its peak power, all the other carriers are at a value of 0. This means the receiver can listen in on one carrier's peak and completely ignore all the others. It's like they're invisible to each other, even though they're all tangled up. It is a ridiculously clever way to pack in data. So what this means is that OFDM gives us the best of both worlds. We get fantastic spectral efficiency, plus it's incredibly tough against those echoes. To deal with the echoes, it uses a neat trick called a cyclic prefix. Think of it like adding a small deliberate pause between your words when you're speaking in a room with a bad echo. OFDM adds a tiny buffer of data to each symbol, which acts as a guard, absorbing any leftover echoes from the previous symbol so they don't mess up the current one. Okay, so OFDM solved the problem of organizing the data, but the second breakthrough, this one was even more radical. It looked at the problem of multipath, those annoying echoes, and asked a totally wild question. What if the problem was actually the solution? And that brings us to MIMO, which stands for multiple input, multiple output. This is the technology that can literally multiply the capacity of your connection, not by using more power, not by using more spectrum, but simply by using more antennas and taking advantage of the space around you. This quote just nails it. It really captures the genius of the whole idea. Instead of trying to get rid of the echoes, MIMO uses them. Every single echo that bounces off a wall or a building creates a unique path from the transmitter to the receiver, and MIMO treats each one of those paths as a brand new, separate data lane. And the hardware behind it is surprisingly simple. As you can see, you just need multiple antennas on both ends. On the transmitter, like your Wi-Fi router, and on the receiver, like your laptop. It's this physical setup that unlocks a completely new dimension for sending data, space itself. This whole process is called spatial multiplexing. Here's how it works. A data stream gets split up, and each piece is sent from a different antenna at the exact same time on the exact same frequency. Now, because each of those signals bounce around the room differently, it arrives at the receiver with a unique spatial signature. The receiver software is smart enough to identify these signatures and tell the streams apart. It's kind of like being able to listen to 3 different people talking at once and understanding each one perfectly because you can pinpoint exactly where each voice is coming from. So how on earth does the receiver actually unscramble that jumbled mess? Well, it uses some seriously sophisticated signal processing and linear algebra. Basically, a lot of math. You don't need to get the equations here, but the core idea is this. The receiver knows the unique characteristics of each spatial path. It builds a mathematical model of the environment, and then, in real time, it basically solves a giant puzzle to reverse the mixing process, perfectly reconstructing the original data streams. All right, now this is where the real magic happens. OFDM is a genius at organizing data by frequency, and MIMO is a genius at multiplying data through space. On their own, they're powerful, but together, they are unstoppable.
It really is the perfect partnership. MIMO takes advantage of the very multipath that OFDM is already designed to be tough against. And at the same time, OFDM massively simplifies the channel for MIMO. It turns a single complex channel into a set of simple parallel ones, which makes all that signal unscrambling math much, much easier to do.
And this is it. This is the whole system in action. A stream of data comes in, it's coded for MIMO's different spatial streams, and then each of those streams is modulated using OFDM before they're all sent out. On the other end, the receiver undoes the OFDM part and then uses its MIMO processing to separate the spatial streams back out. This is the blueprint inside pretty much every modern wireless device you own. And this journey, from foundational research in places like Bell Labs all the way to today's global standards, is why we have modern wireless. This MIMO OFDM architecture is the engine that drives 4G LTE, 5G, and every modern Wi-Fi standard from about Wi-Fi 4 onwards. It is, and this is no exaggeration, the absolute foundation of our connected world. So after all that engineering, what has this amazing partnership between MIMO and OFDM actually built? Well, it's built the world we live in today. The economic impact is just staggering, almost hard to wrap your head around. By making high-speed wireless connectivity not just possible, but reliable and everywhere, these technologies have unlocked trillions of dollars in economic value. They've enabled new services, new businesses, and whole new ways of life that were pure science fiction not that long ago. And the technology just keeps evolving. In our home Wi-Fi routers, we use something called multi-user MIMO, which lets a router talk to maybe a handful of devices at once. But in 5G, things get cranked up to a whole new level with massive MIMO. We're talking about a cell tower that might have 100 or more antennas, allowing it to create dozens of independent beams to serve tons of users in the same area at the same time. It's the same basic principle, just scaled up to an absolutely incredible level. And this right here is how all that complex engineering makes your life better. Faster browsing, seamless 4K streaming, smooth video calls with almost no lag, and a rock-solid connection even in that packed airport. It all traces back to MIMO, creating more lanes on the digital highway, and OFDM keeping the traffic in those lanes perfectly organized. So in the end, the story of MIMO and OFFD is of course a story of brilliant engineering, but it's also a powerful lesson in perspective. The single biggest breakthrough came from looking at a problem everyone was trying to eliminate, those echoes and interference, and seeing it instead as an opportunity. It really makes you wonder, doesn't it? What challenges that we're facing today are just solutions that we haven't quite recognized yet?